Okay, so let's get started. We have our group seminar today by Philipp Höllmer, who is a PhD student at University of Bonn. And when he was a master student at University of Bonn, he came to Paris for an internship in June 2018. He got his master in physics on the subject of all atom event chain Monte Carlo, designing a general purpose Python application in October 2019. And now he is PhD student at University of Bonn. He has paid us many visits. And the last visit was just in February, end of February this year, just before everything closed. And you came back to the carnival that started COVID in Germany, and we went into lockdown. So now we have many meetings here on Weber. And now please get started.
Yes, thank you for the kind introduction. I have to share my screen. Wow, this is going to be funny.
Oh, many people.
Oh,
okay.
Now you should be able to see something, I hope. So in this talk, I'm going to present JeLLyFysh version 1.1, which is basically the next version of the general purpose application we designed in last year, in which I wrote about my master thesis. So this work was done together with Liang Qin, who is also present, with Tony and with Werner Kraut, and of course with Michael Faulkner, who's not here, I think. So I'm sure you all know about the conceptually very simple ECMC algorithm for hard disks, especially after Boutau's talk from 2 weeks ago, but let's repeat it just for introductory purposes. So we assume that we just have a single active initial disk. This disk moves in X direction until it collides with the target disk. So here, and then the target disk becomes active instead. And this process of changing the active disk is called lifting. And this process is repeated for some chain length L, and this distribution of this chain length is an essential parameter of the performance of the ECMC algorithm. Of course, the algorithm, how I wrote it down here, is not irreducible, so it does not cover the whole configuration space. So what we need to do in 2 dimensions, for example, is we need to choose 2 independent direction of motions. So here I just switch to the Y direction. So this you all know, I'm certain, but for our application, we did want to not treat hard disk system, but more general all atom potentials. So I'm just gonna give a short introduction how the ECMC algorithm was generalized to more general interaction potentials. So as a short fact, dropping ECMC constructs an irreversible, rejection-free continuous time Markov-chain. Here the first 2 parts, so the irreversible and the rejection-free, are the reason why it's usually so fast. So irreversible means that even in equilibrium, we have a non-vanishing probability flow in some directions. And rejection-free is, of course, you all know the Metropolis algorithm. There you have the characteristic rejection of moves, and these do not appear in the ECMC algorithm. It is conceived for systems described by continuous variables, and in this talk, I'm going to assume that we have n point-like particles, which are described by the positions, and we take the all-atom approach. So all interaction potentials are just a simple function of these positions. As far as I know, there is no generalization yet for discrete variables. And also it was shown that ECMC often equilibrates faster than their reversible counterparts. I mean, the first example is that Etienne Bernard and Werner Kraut showed in 2011, or solved the puzzle about the hard disk melting phase transition. And of course, Ze, who's also here, and Yoshihiko and Tony also studied the decorrelation properties of ECMC, and I'm sure they're much greater experts in these terms than I am. So you can ask them if you have questions for this. ECMC generally relies on 3 concepts. The first one is a factorized Metropolis filter, which just accepts or rejects the proposed configurations. Then the second thing is the lifting framework, which we use to propose new configurations. And this lifting framework also solves the rejections. And the third ingredient is the event-driven implementation. I'm going to go through these 3 points quickly one by one. So the first point was the factorized metropolis filter, and the general or the basic idea for this factorized metropolis filter is that we can decompose our total potential U, which for the scope of this talk is just the function of the positions of my n particles, into some sum over factor potentials Um. Here we sum over all factors which have a non-vanishing contribution to this potential for any configuration. And then here I introduced this factor configuration Cm, which is just a subset of the total configuration. So this Im here in the back is just the index set of the factor, and these are just some point-like particles, not all of them. So if we want to sample the Boltzmann distribution, for example, then you can directly see that the sum over the factors changes into a product over the exponential weight of this factor potential. So to give you an example, we look at the so-called SPCFW water model, which has a lot of factor potentials, and it is used, or it's an all-atom model we use to describe or to simulate water. The first factor potential we have is that within a single water molecule, we have a so-called bond interaction always between the hydrogen and the oxygen, and this is just a harmonic potential. So this leads to some fluctuation of the separation of these two atoms around some equilibrium length. The next factor is the so-called bending factor, which you can see here. This is just, I mean, when you simulate it, you just get a fluctuation around some equilibrium angle of your internal angle in a water molecule. Then you have two more intermolecular factor potentials. The first one is an interaction between two oxygens and two different water molecules. This is just the standard Lennard-Jones potential, you all know. And the final factor potential is or we assume that all of these atoms in the different water molecules are charged, and therefore all atoms interact via the long-range Coulomb interaction. And this is the long-range Coulomb interaction is usually the bottleneck of these all-atom systems. So this is why this model was also chosen as a showcase. But when I introduce these factor potentials, you can see that we just can write down the total potential as a sum of these different factor potentials. So here I just wrote down the total potential for, now my printer is going on, I don't know what, for two water molecules. What can we use this decomposition of the total potential into sum for? We can replace the original metropolis filter that accepts a change of configuration, C to C prime. So I'm going to assume that we already proposed a new configuration, and I'm going to say how we do this in the next slide. But here it's just about the acceptance probability. And here on the left, you can see the original metropolis filter, which just takes the minimum of 1 and the exponential of minus beta and the total potential change. For the factorized metropolis filter, what we do is we pull out this product here out of the minimum. Of course, as you can all see, that this pulling out of the product in fact reduces our acceptance probability. So this would yield an inefficient or more inefficient algorithm than the standard metropolis algorithm. But what we can use it for is that only the factorized metropolis filter formulates a consensus principle. Because we have pulled out the product here, the new configuration is accepted from all factors independently. So we can express the factorized metropolis filter as a Boolean expression, so to say. So here we have the question whether the new configuration is accepted by all factors. And this is answered by Boolean conjunction over all factors. And we ask each factor statistically independent whether the new configuration is accepted by this given factor. And this we can do, of course, by checking the acceptance probability of just this factor. And just to repeat, each factor only depends on a very limited subset of our full configuration. So now that we know how we can accept new configurations using the consensus principle, we have to ask the question, how do we propose new configurations? And for this, we use the so-called lifting framework. The lifting framework is a very general principle in statistical mechanics, I think. But here, for our purposes, we just augment each configuration with auxiliary variables that resemble the velocity of Newtonian mechanics, but should not be confused with this velocity. What does this mean? For each configuration C, we choose a single active particle with some velocity v, and this we write as the C, A tuple. Then we say, if we have this configuration CA, that the proposed configuration from CA is always C prime A, and in this C prime, I just moved my active particle by the velocities times some time step. So as you can see, this lifting framework allows to persistently move into one direction without introducing like forbidden probabilities which depend on more than one previous configuration. And this is why it usually yields better mixing times, if you do it correctly. Now we have our proposed configuration, and as I said, then we ask the factorized metropolis filter if the configuration is accepted or not, and then two things can happen. So here on the left, I draw two particles which interact by some factor potential, and I chose one as the active particle. And we now propose the move that one is displaced by v delta t. Then the first thing that can happen is the factor potential between these two particles just accepts the move of the first particle. Well, then nothing fancy happens. We just displace the active particle and we continue. The active particle is still active and it just continues to go into the same direction. However, it could also happen that the factor potential, this is the lower case here, rejects the move of the first particle. And as I'm going to say in a minute, or as I'm going to say now, is what we need to do then is we need to do these lifting moves, which I already showed in the hard disk example. So then we do not displace the first particle, but we change the active particle to the second one, to the other particle, which was involved in this factor potential. So this is basically a lifting move. Just to highlight, so what we achieve by this lifting framework is that the active particle moves persistently until one given factor breaks consensus. Of course, the active particle has to participate in this factor. And then if you have a distance-dependent pair factor potential between A and T, we have to do these lifting moves. A lifting move changes the active particle from A to T, but the target particle then has the same velocity. So it continues to go into the same direction. And these lifting moves thus replace the characteristic rejections. One can then do the math and check everything, and then one finds out that maximal global balance is only satisfied for infinitesimal time steps dt, and also only for distance-dependent continuous interaction potentials. So you can expand these lifting framework I just presented for a two-particle factor potential to an n-particle factor potential. Then the lifting just gets a bit more complicated. And just to say, maximal global balance is essential for a Markov-chain because this basically says that we sample in the long time limit, we sample the chosen equilibrium distribution. What do I mean with maximal global balance? It means that if we have a flow from some configuration A to some other configuration B, that the inverse flow always vanishes. And the other characteristic is that there are no rejected moves. However, you see a problem here. I said that we only satisfy this maximal global balance for infinitesimal time steps dt. This means if we now naively implement our ECMC algorithm and just say, okay, I take my active particle, displace it by velocity times delta t, then check for all factors whether they accept it or not, and then carry out the lifting move or not. This would first would yield a very slow algorithm because I have to change or check all factors all the time. And second, it would yield an technically inexact algorithm. So I have to choose my delta t very small to get more exact and exact. Both of these problems are finally solved in the event-driven implementation. So instead of choosing this time-driven implementation, we sample for each factor m, which includes my active particle, so-called candidate event time, delta Tm. So in this candidate event time, so I have my starting configuration here, and then I sample some candidate event time, which corresponds to some final configuration where my active particle is displaced using this candidate event time. And it turns out what one needs to do is to use this equation here. So what we consider is that the beta times the positive potential change, this is this plus here, between these two configurations must be equal to some random number and minus the logarithm method. So this is basically an exponentially sampled random number. What do I mean with positive potential change? It just means, okay, I have my starting configuration, then I move my active particle. This will change my factor potential somehow, but we only consider the rising potential changes, not when the potential change go down. You can imagine it like your particle has some energy backpack, and only when it wants to climb a potential hill, it has to use energy from its backpack. But when it goes down some potential hill, it can just go freely. And when all of its energy is used up, then we do the lifting. Of course, my active particle is not only involved in a single factor m, but it can take place in several factor potentials. And then I have a candidate event time for each of these factors, and then my final event takes place at the minimum of this candidate event time. So to show you some pictures, which might explain it a bit more clearly, here on the left, I plot on the x-axis the displacement of my active particle. So Vx times the delta t, I assume it goes in x direction. And on the y-axis, I just plot the beta times the potential change of some potentials. So the blue curve is in fact the sum of two other potential changes, and this is just the yellow curve and the green curve. Now I can do several things because I have a certain freedom in choosing my factors. The first thing is I directly take the blue curve. This is done here on the right. So the blue curve is just repeated, and the red curve then just plots the positive potential change instead. So you can see I start together with the blue curve as long as the blue curve is rising. Then at the point where the blue curve goes down, the red curve stays constant, and then it goes up again together at some point. What I need to do then, in principle, is just take a sample my random number here, then check where it hits the red curve, and this gives me my candidate event time. However, I said the blue curve is the sum of two other curves, of the yellow and green curve. So what I can also do is I sample two statistically independent candidate event times. So here for the yellow curve, which is just increasing all the time, here I take an exponentially random sampled number, check where it hits the yellow curve. This gives me the first candidate event time. However, I have to do the same for the green curve. So the green curve is here, and the red curve is again the positive potential change of the green curve. So I sampled another random number and check where it hits the red curve, and this gives me another candidate event time. What I need to do then is compare these two event times, and I only consider the smaller one. So in this case, it would be the first factor, and then I carry out my lifting move in this first factor, and I just neglect the second factor. Sure, this is not the whole story, because for an irreducible Markov chain, that means that for a Markov chain which potentially covers the whole configuration space, the direction of the velocity has to be resampled after some chain duration. Or if you take a constant velocity, you can also say after some chain length. And of course, in how many independent directions you go depends on your dimension of your system. This is not the full story, because these potentials can in fact be very difficult or very complicated looking. Take, for example, the Coulomb interaction potential in some periodic boundary setting where it involves quite complicated eval summations. Then the integration and inversion of my continuous potential change. So what I mean is that I have my random number here, and I have to check where it hits the positive potential change, can be difficult or even impossible. This is then usually solved by bounding potentials, and the characteristic, or what I need for a bounding potential is that I draw one down here, is that it rises always more steeper than my original potential. So I have the red curve, which is my original vector potential. Then I have the dotted red curve, which is the positive potential change. And you can see that the bounding potential, the black curve, is always more steeper. And the steepness, so to say, we call the event rate, by the way. Then I can use this bounding potential to compute my candidate event time, which exactly happens on the left here. However, as you can see, because my bounding potential is always more steeper than my original potential, I will on average, or I will always sample event times too early. And this is solved by confirming these events of bounding potentials afterwards. So sometimes the proposed events by the bounding potential are accepted, but sometimes they have to be rejected, unfortunately. This is sketched on the right here, and you can show that the necessary confirmation rate of this proposed event is just the ratio of your two event rates. So the ratio of your steepness of your potentials at the given sampled point. And just to mention another thing, which is very important, the cell-veto algorithm. The cell-veto algorithm then uses, in a very clever way, the cell-based bounding potentials. And so what do I mean with cell-based bounding potential? This is sketched here. So assume we have some cell occupancy system which maps all particles onto a given cell. So here we have the active particle in the cell C1 and the target particle in the cell C2. And then we pre-computed upper bounds on the event rate for any position of the active particle in C1 and for any position of the target particle 2 in its cell. Because we pre-computed, we can just use this this constant event rate in a very easy way. Of course, that's not the full story for the cell-veto algorithm, but then the cell-veto algorithm cleverly combines several cell-based bounding potentials. This is the fact, or this is the idea which then reduces the overall complexity of our ECMC algorithm to a constant runtime per event, because we can just reduce. I mean, if you just take without the cell-veto algorithm, you would need to check all the time every factor where my active particle is involved in, or I have to compute a candidate event time. So for long-range interactions like the Coulomb potential, I have always like n factors I need to compute a candidate event time. But this cell-veto algorithm then reduces this to a constant number of factors I have to consider. And of course, it was designed by Sebastian Kapfer and Werner Kraut some years ago. And you can read more about it on the internet. So this concludes my short introduction into the ECMC algorithm. This is all you need to follow the rest of my talk, I think. So, but as you have seen, that the time evolution of ECMC is fully determined by a time series of events. This makes sense because it's called event chain Monte Carlo for this reason. In our application, we then say that an event consists of an event time, delta Tm, or a candidate event time, and an out state. What do we mean with an out state? Or let me first say the next point. And these events are computed in our application in event handlers based on an in state. So what do I mean with in state and out state? In our in state, we have our active particle A and the target particle T, for example. I mean, it's just the subset of particle, or the positions of the subset of particles which contribute to the given vector potential. Then in my out state, I computed the candidate event time, and in my out state, I imprint the lifting move. So there I displaced my active particle by the candidate event time times its velocity, and I changed the velocity to the target particle. Of course, I compute several events and several event handler instances, and only the out state of the earliest event is then committed to our global state. So the global state really stores the full configuration of all our particles. Then we introduce two things. The first things are the known factors, which I talked about in this talk a lot. So the events of factors are just required for the global balance condition. And this is shown in this short sketch here. So we have our in state here on the left. there we assume that this depends on 3 particle positions, and 2 of them are now active. Then our event handlers in between, it uses some random elements, so it samples the exponentially distributed random number. And in our out state, the 2 initially active particles are displaced by v times the candidate event time, t event. But I also carried out a lifting move. So now 2 other particles are active. However, that's not the full story, because we also need to introduce pseudo-factors. These pseudo-factors complement factors, but they have no incidence on the global balance condition. One first example, which you can easily think about, is the so-called end-of-chain event. I mean, we just need it for the irreducibility of our Markov-chain. But we can express it as an event, and we can also compute it in an event handler. So here, take the end state. We have 1 active particle, and in our end-of-chain event wants to change the direction of motion and also change the beginning active particle of the next chain. So this is our end state. Then the event handlers in between, and it just computes the event time where the end-of-chain event should happen. And also in its out state, it changed the active particle, and it also changed the direction of motion. But this is just one example. In our application, we express everything as events, or by using these pseudo-factors. So other examples are like we have sampling events, or we have the start of run event, which just starts the run of our application, or we even have an end of run event, which just ends the application. And by using this idea of these pseudo-factors, we basically really achieve that we can express the time evolution of our application fully in terms of events. And this is then shown in this beautiful sketch. So we start here with some trajectory. At some point, we have an event which changes our trajectory, and then we have another event at B. At each event, we have to compute new candidate event times and trash old ones, because they are not valid anymore, because we just changed the active particle, so to say. However, usually some already computed events do not depend on the active particle at all. Take, for example, an end of run event where I just say I want to run my simulation for 1,000 angstrom, then I can just keep it forever. So this is sketched by this A3, which is never trashed at any event. And yeah, this just shows our trajectory of our simulation in the application. The event handlers are a very central element of our JeLLyFysh application. However, they are not the only element. On this slide, I want to show you all of the elements of our JeLLyFysh application. And what we chose as the basic design pattern is the so-called mediator design pattern. What does this mean? It means that all our elements of the application, which I will introduce shortly in a minute, delegate their interaction to the mediator. Why is this good? Because it means that this design is usually very easily expandable, because you can just add new elements and expand your mediator with the interaction. And also it's very, you can easily change the elements independently from each other.
And if I may say that at some point, so we had a discussion of how we would set up this whole thing. And then you came up with the idea that this was actually a design pattern, and that there was a famous book written. So maybe you can explain that. So
there is a, I don't recall how this book is called, but it's somehow by the Great Four. So there's a very famous book by design patterns it has nothing to do with physics. It's just for software architecture. And there you can read through it and then check which design pattern just matches your desires, so to say. And because we needed this easily expandable design, we just chose the mediator. That's what I can say. I can send you a link of the book afterwards. It's very interesting if you have to. It's very interesting in a software architecture way, I think. But this design pattern, if you take it serious, the mediator then only contains the interactions between your different elements. But in our case, it also contains the main iteration loop of ECMC. So what do I mean with this? This is shown in the sketch here in the red box. So our mediator in the first step always extracts the active global state. This means we just check which particle is active right now. Then in the second step, it gets the event handlers which need to compute new candidate event times. The third step then gets the corresponding instates for these event handlers. These instates are then handed to the event handlers, and the event handlers can then compute their candidate event times, and these are requested by the mediator in step 4. In step 5, then some other element determines the shortest of these candidate event times. And in step 6, the mediator can use the shortest event time to go to the corresponding event handler and get the corresponding outstate. Step 7 commits this outstate, and step 8 then is responsible for trashing events which became invalid. For example, if my active particle changed, I trash all factor events. Step 9 is optional because sometimes after, for example, sampling events, I want to really sample something. So this is then the output part. As I already said, all these steps for these steps, to achieve these steps, the mediator communicates with other elements of our application, or just calls methods of them if you want. And I'm going to go through them one by one now and describe their abstract actions. So the first element is the activator. The activator, as you might guess, determines event handlers which should be activated. So event handlers which should run or which should compute new candidate event times, and it also determines the instates. For this, it uses the active particles. It also, so this is used in step 1, the activation. Also, after an event is committed, it determines the events which should be trashed and which became invalid, so to say. So this is step 8 down here. For these actions, the activator may use an internal state, for example, a cell occupancy system. And the cell occupancy system then helps, for example, to determine nearby particles of the active particle. The next element is the so-called scheduler. The scheduler stores all candidate event times, which the mediator requested in steps 4. So it requests the candidate event times and hands them to the scheduler. And it also stores like the pointers to the corresponding event handlers. In step 5, it then determines the earliest candidate event time. The next main part of our application is the state handler. So the state handler stores the global state of our system. So we divide it in the global physical state, which is just the positions of all our particles, and the global lifting state, which are the velocities and the timestamps of our active particle. So why do we separate it like this? Is because it's usually the global physical state is much larger than the global lifting state. So we have a position for all our particles, but in our first versions, only a single particle is active at any time. So this is why we don't store it as one. Surely, it also extracts the instates from this global state, which are needed by the event handlers, and it also inserts outstates. So this is relevant in step 3 and in step 7.
And just if I may say, so here you see also, I mean, we have this mediator design pattern. So it's kind of the central block, and the elements that have to handle the event handlers, they don't even have access to the million or so particle coordinates of the system.
Yes, right? And this is where it becomes important that each event only depends on a very limited subset of our very huge configuration, so to say. And this also implies that our event handler can do whatever he wants with his subset of positions to just determine this next event. Yes, so this is also another reason why we chose this mediator pattern. The final part is the I/O part, or the input-output handler. So the input part is at the beginning of the run. It creates the initial global state. It creates it randomly or reads it from a file in some file format. And the output part, which is relevant in step 9, it samples observables. So take observables as a very general phrase here. It might also just be that it dumps the whole configuration into a file, but it can also be that it samples the polarization, for example. So in this output part, there you can have considerable amount of computation. And just I mean, these are just the abstract, or let me say one more thing. Here on the right, we have our event handlers, which I introduced earlier. So, and as I said earlier as well, that in principle, the event handlers compute statistically independent events. So this also means that in principle, we could run each event handler in parallel, so on a multiprocessor platform, for example, because then each event can just compute an event. And this is why we have these red dashy boxes. So in this design, we have all these things on one processor, and each event handler has its own processor where it computes events. And on this slide, I just described the very abstract actions of each element. And you can read more about how we implemented for the all-atom case in our design paper. However, I want to express a bit more on how we treat the global and internal state for our all-atom simulations. So how do we treat the global and internal state? For our simulations, it turns out that it is very nice to represent composite point objects as trees. And for this, we created the state handler, which is a tree state handler. So composite point objects you can think of as molecules, for example, molecules with atom positions below. And then the molecule position is just the average of its atom positions. And as I said before, the global lifting state only stores velocities and timestamps for the active units. So here on the left, we draw a composite point object. And on the lowest level, you can see like, I think these are 9 atoms with different charges, which are shown or differentiated by their color. And then we combined different subsets of our atoms to composite point objects. So here on the right, we combined these 3 atoms to a composite point object. And this composite point object is then described by the average position of its atoms. The same we did here on the left for these 4 atoms. And then we have an overall composite point object for all atoms. And this you can just draw as a tree instead. So this is what we've done on the right. So on the lowest level, on the leaf level of our tree, so to say, we have all our atom positions, and then different atoms are combined to different composite point objects, and then you just construct your tree. This tree structure allows to choose active units, independent active units on different levels of our tree. So what we can do on one hand is, okay, we choose an active atom down here, which moves with some velocity, and this will induce some motion of its composite point objects to which it belongs. So this is the right branch here. What we can also do is to not choose the atoms active, or to choose 4 atoms active, but we can just say, okay, let's just make a composite point object active here with V. And this will then induce the motion of all its atoms and also of the composite point object it belongs to. Another great thing we can use this tree state for is in our internal state. So in our current version, the internal state consists mainly of cell occupancy system, which is used for cell-based bounding potentials, basically, and for the cell-veto algorithm, and also to detect nearby particles. However, this tree-based composite point objects allows to not only track atoms, which is done here on the left, but we can also track the average positions of full molecules very easily. What we can also do on the atom level is not just track all atoms, but we can just track atoms with a given charge. So in this example here, we did not track the blue atoms, but the red atom, only the red atoms. So this, we have a great flexibility in our cell occupancy by using this composite point objects. And if you paid attention on the previous slide, you may have noticed that the global state is stored in our state handler, of course, so these trees. However, the internal state is stored in the activator. This is because the activator usually uses the cell occupancy system to determine factors which should be activated. So we have, so in order to keep both states consistent, we again use pseudo factors. And in this case, it's just a cell boundary event, which we can express again as an event. So we have an in state, which is an active particle. Then we have an event handler, which is a pseudo factor in this case. So in this event handler has only access to the cell system, not the cell occupancy system. And then in the out state, it just it just computes the time where my active particle hits the next cell boundary. And if this event is then committed to the global state, this will also trigger an update of our internal state. So this is how we keep both states consistent in our application. Now that you've learned all about our general architecture of our applications, I want to present to you how you actually run it without coding Python yourself. For this, we use configuration files in the ini file format. And these ini files then specify physical and algorithmic parameters. So what do I mean? It means the temperature, the system size, the number of particles or atoms or molecules you want to simulate, the factors which you want to consider, the pseudo factors you want to consider, etc. And if you don't know this, an ini file consists of so-called sections, and these sections are always started by these, what do we call it, edgy brackets. I don't know. And within a section, you have these property and value pairs. So properties on the left and values on the right. The only obligatory section in our ini file is the run section. And in the run sections, you must have, or you have to have two properties. The first one is the mediator property, and the second one, the setting property. So you might guess the mediator property chooses the mediator you want to choose to run your simulation with. So here in this example, I just chose the single process mediator. We have another one, which is the multi-process mediator, which then uses, or then where each event handler uses its own process, as I described earlier. The other property, the setting, expects the setting you want to use. So in this case, I want to use the hypercubic setting.
And so just to indicate what, so we have this beautiful parallel, right, multi-processing version. And it's really beautiful, and it considerably slows down the whole program, right? At the moment, we have
due to Python problems, because Python actually has. You cannot have threads in Python like in C++, for example, like Botau did, but you have to really spawn a new process every time so that they can run in parallel. Then the communication between our processes, where I send the in states around and I send the out states back, really limits the performance. So if you really want to do this more efficiently, you have to use C++, or I think even Go, as Tony mentioned some time ago, which has very lightweight threads. Of course, this is not what you can see here is not the full configuration file. You have to specify more properties of our single process mediator, for example. And we do this by then constructing kind of a tree structure within our configuration file. So another section in our configuration file then corresponds to this single process. So here it's in snake case, and then we have another section in camel case. And within this section, then you specify all properties of our mediator. So here we choose the state handler, the scheduler, the activator, and our input-output handler. And just as a side note, where does these property names come from? These are just names which appear in our code. So each section corresponds to a class of our JeLLyFysh code. So somewhere in our code, in its own file, we have a class single process mediator, which inherits from a mediator because it's a mediator. And then the relevant method you have to look at is this initialization method. So this is, if you don't know Python, it's the constructor of your Python class. And then you can see this initialization method expects 4 arguments, and these are exactly the arguments which appear up here in this properties. So the input-output handler, the state handler, the scheduler, and the activator. And this is, this is also how our factory then uses this configuration file to build the whole run of the application. So let's go through this example a bit more. So I now just said which properties should be used in a single process mediator. And I have to do the same, of course, for the hypercubic setting. So here I chose a hypercubic setting with a system length of 1 in some units, beta of 2, and in 3 dimensions. And then I won't go down the full configuration file here because it would get quite lengthy, but I will go down one path. And I think the most relevant path, because this is the path where the factors are chosen. In fact, the factors and pseudo factors I want to simulate. So here we go into the activator, which is in our case the so-called tag activators. And this tag activator expects some taggers. I won't tell you more about it, but just take it for granted now. But these taggers correspond to the factors we want to simulate in our simulation. And then you might guess, okay, we have a Coulomb factor. So this simulation, and we have a sampling factor, an end of chain factor, start of run, and end of run. So this simulation or this configuration file I show you here is actually very simple because we just take particles which interact only by the Coulomb interaction. This is the only real factor we have here. The other 4 things are just pseudo factors. So I want to sample something. I want to resample my direction of motions. I want to start my run, and I also want to end the run. But let's follow down the Coulomb path a bit more. So we go from here to the Coulomb section, and then you can see that, here the create and trash appears. This just means that after I have a Coulomb event, I want to trash all Coulomb events I've computed before. However, the real important part is here the event handler. So in order to compute events for my Coulomb event, I use the 2-leaf unit bounding potential event handler. What does this mean? It means just that this event handler can treat interactions between 2 atoms, and to treat this interaction, it uses a bounding potential. This is specified in the 2-leaf unit bounding potential event handler, and you can see here it uses some bounding potential to sample the candidate event time. And then when it's asked to compute the outstate, it uses both the bounding potential and the real potential, which in this case the merged image Coulomb potential, because we are in the periodic setting. And then it computes the event rates of the bounding potential and potential and accepts the proposed event by using the ratio of the event rates. And yeah, I have taken you through this example.
So it's done. It doesn't go any farther.
No, why it didn't go any farther, and it does not go actually, because then from here the merged image Coulomb potential does expect arguments in the initialization method. However, it has default arguments, and in this case we just want to use the default arguments, so we do not specify them any further here. So this is actually the end of the path of this tree, if you want. But as you've learned, you can also just then draw, instead of having your configuration file, which might get quite lengthy, you can draw it as a tree if you want. So we start with the run section at the top, and then we go down the tree one by one. So you saw the single process mediator section at the hypercubic setting. The path we just took is went here, then we went to the tag activator, then we went to Coulomb, and then we went to the event handler, and then you saw these two potentials here. But as you can see, I haven't shown you all of the cases, but there is a lot more going on. So
and just to say that, so this makes a configuration file with about like 200 lines, and it's completely explicit. And Young and Philipp have written this code, and we are using it. And so then when we want to run things, in fact, it's very easy to change things and to adapt them, because
I mean, if you just want to use the code we provide, you actually don't have to code any Python yourself. You just have to change parameters in these configuration files. Of course, because it's always nice to have example, our first version already ships, so JeLLyFysh version 1 ships with several exemplary configuration files for standard all-atom simulations and a cubic simulation box with periodic boundary conditions. And the cases we cover are the interacting charges. So what you do there is, or in our examples, you have two charges with the same charge in a periodic box which interact. The other case is dipoles. And the last case is the SPC-FW water molecules, which I introduced earlier. And so that you don't have any excuses as to why you weren't able to run the simulation, I prepared a short video on how to actually use this exemplary configuration files for the case of the interacting charges. So this was the configuration file I described before. So let's start the movie. I hope it works. So here in the first line, what I do there is I just clone the public repository, which can everybody do. So it's public. Then I go into the cloned repository. These lines are optional. There I just create a virtual environment, in fact. And you might note here that I don't use the standard. Oh, wait, pause it. I don't use the standard CPython interpreter, but PyPy. What PyPy is basically adds a just-in-time compilation to Python. And it turns out that for object-oriented code, like we do it, it's very high performance. So I think it made our code like a factor of 10 faster. So this is why we really like PyPy.
And this looks very easy, but you have to have the correct version of PyPy and then of gfortran and of there are lots of little programs that have to be installed correctly. And only once you have done that life becomes easy. Before it, it's horrible.
I mean, it's not that's not completely true, because for this example, or for all examples we show on we ship, you actually really just need the
Oh, I see. Okay.
So we don't, I mean, in our next version, you have to have some additional packages, which might be a hassle to install, but we help where we can. But
so for the published version, it's only the PyPy that has to be correctly installed, right?
Yes, and this is usually, I mean, if you have Mac, you can just install it by using Homebrew, or if you have Linux, I recommend to install it via apt-get. And for Windows, there's certainly an executable on their side. So this is actually very simple. And you can see it because here, if I create a virtual environment here, this is just a clean new virtual environment where there aren't any packages installed. So I activate it here. So here in this, sorry, I did mess up. So we have unfortunately two, I think. Yeah, we have to wait until it comes to this place again. But yeah, I mean, I will show later. I will show another movie where I show how it's done for the new version. But it's still very simple, in my opinion. I mean, these are just the usual installation complications you might sometimes have. So. Okay, now it's back where I want. So in our repository, in our public repository, we have a source directory, which I went into. And in this source directory, we have the so-called run.py script. And this I executed here with the help option. And then you just get the usual help. And as you can see here, this run.py script expects one positional argument, which is just the configuration file. And then you have several optional arguments, which I won't go specify any further, but I think they're pretty self-explanatory. So what I'm going to do now is I'm going to use this run.py script with the configuration file I just this I just described on the slides before. So this is in some directory, and you can see by the directory names, it simulates Coulomb atoms, and it uses in bounding potential. And then the simulation runs. And during the simulation, it samples some quantity, I'm going to explain in a minute, and it creates a .dat file also in the repository. Also, if you've looked closely, you might have seen that the simulation started very slowly. So this is the time where the just-in-time compilation of PyPy was not used yet. So this is approximately the time it would take in a standard C Python interpreter. But then it has a huge boost up where the just-in-time compilation kicks in, and it just gets a lot faster. So yeah, this was a very short example on how to run the exemplary all-atom simulations. And as I said, if you run this simulation, it will actually sample the pair separation between your equally charged charges. And here, what we plot here is the CPDF. So we also ship a plotting script to create this plot. And here we plot the CPDF for different methods. So the very first one is the reversible Markov-chain Monte Carlo, so standard metropolis algorithm, just to compare our numbers. And the second one is exactly the simulation we just ran. So it's the inverse power. It's the simulation which uses an inverse power Coulomb bounding potential to treat the Coulomb factor. The third method is where we use the cell-based bounding potential instead. And this is the intermediate step to finally treat the Coulomb interaction by the cell-veto algorithm in the fourth method. This is just the interacting charges case, and we do basically the same for the dipoles and the water molecules. And just to highlight it, our examples that all include the long-range Coulomb potential, which is often the bottleneck of these all-atom simulations. Then all the simulations treat different sets of factors. So sometimes it's just straightforward 2 atom factors. Sometimes it's factors between 2 molecules, which involve quite complicated lifting schemes. But in our configuration file, you just have to say, use this lifting scheme, and that's it. Our examples also use cell occupancy systems on both the atom and molecule level, and we even have a case where both cases, or we have a cell occupancy system for both cases simultaneously. And also we treat the intermolecular Coulomb and the Lennard-Jones potentials for the case of the water molecules by the cell-veto algorithm. The last simulation I want to highlight is the simulation which changes between atomic and molecular motion. Because I said earlier, our tree structure in the global state allows to easily make full molecules active, so full composite point objects. So here on the left, you have the standard case where one single atom is active, and this induces some motion of the molecule it belongs to. So this is just the dipole case. But then in our simulation, we changed from this mode to the other mode where one full dipole is active. And this induces some motion of our two atoms. And to show this in a bit more detail, now not for the dipole case, but for this SPC FW water model. Just to remind you, the SPC FW water model includes a bond factor in a single water molecule, a bending factor, a Lennard-Jones factor, and a Coulomb factor. Let me move this away. And so I've created the configuration file and set up the script to change between these modes. And in the following, here on the right, you can see the initial configuration, which was actually created randomly. So you have two water molecules just being at random places. And now in the simulation that will follow, I will always just go into the positive X direction. And I will start in the standard case where always one single atom is active. You can see here the upper one moves first, and then inside the water molecules you have kind of this wiggly. But at some point, at some point, I think at half the simulation, I will change. I mean, we have this also these intermolecular lifting moves. Here, I just changed to the molecular motion instead. So now we suppress this wiggling motion and just move the full water molecules forward. Of course, you cannot only do this full water molecule motion because we never sample the degrees of freedom inside of the water molecules in this motion. So you always need to switch these two modes to really get an irreducible Markov chain. However, it might be that introducing these molecular motions might yield faster decorrelations for water simulations. And this is what we're studying at the moment.
I need a GIF. I need a GIF of this to put on my website.
I can provide it.
It's really nice. This when they kind of walk to the right, that's really too beautiful.
Yeah, and of course you also saw the periodic boundary, but I think you can. This was all I want to say about version 1.0, and I want to do a short slide at least to the 1.1, where we have some pretty exciting changes. Although these changes are not conceptual changes, but most of them are for speed purposes only. So the first thing we changed is that JeLLyFysh version 1.1 is not installed by cloning the repository, then going into the directory and doing everything itself, but now we use setup tools. These setup tools on the one hand create executables, so we get rid of this run.py script, so to say, but it also compiles C extensions. So in these C extensions were actually the first place why we needed the setup tools, because we didn't want to ask the user to compile every C extension we have themselves. So which C extensions do we have? It's the Coulomb potential, we now fully implemented in C, and the scheduler as well. So although our PyPy uses just-in-time compilation, it turned out that really implementing the things in C is still a lot faster. So I mentioned the setup tools here. This is, I like to say, this is the standard way to install Python packages, by the way. So this is, if you know pip or conda, this is what is used under the hood. And I created another movie just to show you how it's done in this new version, which is not publicly available yet, but which will be at some point. So now it changes a bit in the beginning. So I just created a fresh new directory where I want to work in. Then I create my virtual environment again. So this is again a freshly installed PyPy, so without any packages. This always takes a bit. So now I activate it. So here is the first thing. I mean, every Python interpreter ships with this pip, and here I just install pip setup tools and another package, which is important to install things. But these are usually installed in your interpreter. But these are just necessary pre-steps. But now the most important steps come, and this is here. So here I then use the same pip to install a local repository. So this is not public yet, so I cannot point it to some internet address. So I just cloned our private repository, and I just point the pip to it. But at some point we will allow to just, I mean, then you can just call pip install JeLLyFysh, for example, and then you can install it from the internet directly. And what this command will do, it will compile all our C extensions, and it will place our code in some internal directory. And this code is then always found by our interpreter. And this also solves the problem. So you can see here successfully installed JeLLyFysh and some other dependency. But this also solves the problem that in the first version, you actually had to go into our source directory and execute the run.py script always from this directory. Otherwise, Python does not find the code. But now this is all solved automatically. So wherever you are, if you use the interpreter you've installed JeLLyFysh on, you can always find our source code. It's always importable, so to say. I also said that this setup tools allows to create executables. So one of these executables is the JeLLyFysh examples. So I just executed here. What this does is it creates a directory called JeLLyFysh examples, and it copies all our configuration files we ship with our JeLLyFysh application into the current working directory. So I go into this directory, which was just created, and then I use the JeLLyFysh --help. And this JeLLyFysh executable is basically the run.py script you saw already before. Then I just do exactly the same simulation as before. So again, the power-bounded.ini, and with some verbose option, and then it starts to calculate again. But now it uses C extensions under the hood. And as you can see in the end, I mean, if you look closely, you saw that the first version took like 14, 15 seconds, and this one now takes 9 seconds. This is partly due to our C extensions, but also partly due to another fact or a great change we did. And this is the handling of rejected events. I mean, I introduced you earlier to bounding potentials, and I said that for bounding potentials, you need to confirm or reject events. However, in our first design of our mediator, you saw here in step 6. So in step 6, this is where the event handler computes its outstate, and it also determines whether a bounding potential event is actually rejected or accepted. And this is imprinted in the outstate. Either you have a lifting move or you have not. However, the mediator just does not care, and it always commits the outstate to the state handler. And it always asks the activator, which events should I trash? So this is, if I have some rejected Coulomb event, I always trash all other Coulomb events, even though nothing changed. I mean, the active particle is still changed, still the same, so that I could, in principle, just keep these events. So what we do in the new version, here on the right instead, is after we request the outstate, we check whether the outstate is none. And an outstate equal to none just means that the event handler just computed a rejected event. If this is the case, we compute the candidate event time again, only in this event handler, which just computed the rejected event, give it back to the mediator, and then we check again in using the scheduler, which is the shortest event time. So we introduce this extra loop, which loops until there's a real accepted event, which actually changes something in our lifting state.
And in mathematical terms, if I just may say that in mathematical terms, we are doing what is called the thinning of an inhomogeneous Poisson process.
Yes.
And what you are doing, what you are explaining here is that, so in this thinning, it means that sometimes the inhomogeneous process doesn't have events that the homogeneous process that is used on top of it has. And here you just have this wonderful shortcut that keeps you from doing the whole calculation again.
Yes. Yeah.
It's thinning of inhomogeneous Poisson process.
Yes. This is what I expressed sloppy as we sample events too often if we use this bounding potential, and then we have to throw away some of them to actually get the desired behavior in the end. But yeah, why does this actually help? Because after now we have the rejected event, we do not trash everything and recompute everything, but we have this shortcut. And this is very essential in the cell-veto, if you use the cell-veto algorithm, by the way, because usually you have a lot of rejected events if you use the cell-veto algorithm. And this is what allows for the first time also to simulate up to 10,000 water molecules using the cell-veto algorithm. So before in version 1.0, it was just not possible. And this, I mean, if I approximate the speed up to like factor 10 to 15 or so for 2, and then, I mean, yeah, it was just not feasible to do it before, and it's possible now. So that's good. And I mean, these are the 2 huge changes, so to say. But however, we have some more minor changes. The first thing is that we can now write a trajectory of a simulation in DCT files. So this was, I cheated a bit before, so this was actually used when you saw this movie of the motor motion. So I used version 1.1 there, not 1.0. But this allows to create movies and to look at trajectories in a bit more detail, which might sometimes help. And we added more event handlers, more sampling and output handlers, more estimators, which are used to estimate cell-based bounding potentials, and more things in general. But these are all small things. And of course, the last thing, we added more unit tests. We fixed a lot of doc strings. We fixed some bugs. But these are just the typical things you notice if you work long enough on an application. So let me conclude my talk with a summary slide about the JeLLyFysh application. This is the logo, by the way, beautifully designed by Liang. JeLLyFysh implements ECMC for a wide range of all-atom systems. Right now, we ship with exemplary all-atom simulations, which treat interacting atoms, dipoles, and water molecules, but it is intended to eventually treat peptides and polymers. The design is chosen such that it's easily expandable toward new interaction system shapes, and its general architecture is suited to treat other models. So although right now we implemented everything, for example, our state handler for all atom simulations, you could in principle easily write a new state handler to treat spin models. This might interest Yoshihiko, for example. And by this, we hope that it will at some point foster the development of irreversible Markov-chain algorithms, so that not everybody goes home and writes his own code, but that you have a central place for where ECMC is used. In its version 1.1 and also some of it in its version 1.0, we implemented ECMC for homogeneous translation invariant and body systems in a regularly shaped periodic simulation box. We included the long-range Coulomb interaction, and factors can optionally be treated by the cell-veto algorithm. And it's also based currently on configuration files in the ini file format. However, the work is not done, and the biggest obstacle we still have to climb, so to say, is in future version is that at some point it would be nice to include an arbitrary number of active particles, starting on a single processor, but it would also, of course, be nice to have it in a parallel treatment. So this was work which was started in the talk by Butao 2 weeks ago. So yeah, and that's it for my talk. That's all I wanted to say. So thank you for your attention. And if you have questions, I'm happy to answer them.
Okay, thank you very much. Thank you for this very nice talk. I put a little bit of noise here. Okay, thank you. If I make just one comment, it was also, I mean, for us, it was the first. I mean, I think I can speak in the name of Tony also. For us, it was the first case after many decades of coding ourselves and coding Solala, of seeing some real systematic code development. And we have seen it over the last months, because many times we have been asking whether many times we have said that this or that feature that we had was a bug, for example, but there is this whole framework of first of all of this design of an application, and then the framework of unit tests and all of that has made this application extremely bug-free for the moment, right? So we have not suffered from a single bug. So now, please, questions.
So the thing I was thinking of during the talk is to what degree one might be able to regroup the factors during the. So this is of course going on. This is JeLLyFysh 1.2, not 1.1. The factors can regroup, and linking into what we did with Z is to what degree one can interchange factors Because what we discovered with was that there are certain situations where the code can be inefficient, and by shifting things between, because the decomposition into factors is very far from unique. You just have to have a sum of things which are equal to what you want, and you can break up the sum and shuffle stuff backwards and forwards as much as possible. The question is to what degree one can easily shuffle things between different parts of the separation within the machinery as it is now.
I mean, you mean within a single run? I mean, usually, right?
Essentially, regrouping factors. How to what degree one can regroup factors. This is of course linked to even Werner's messages overnight of being inspired with what we found with CERN.
I mean, right now it's true that we choose kind of a fixed factor set in the beginning. Although what we started with this molecular motion is that you can kind of, I mean, our activator in fact allows in some way to actually change your factor sets because it has this activate, it has some activate and deactivate. So it can activate certain factors and it can deactivate other factors. So you could do that. However, the downside is your configuration files would get pretty long in the current version. But at least I don't know right now another way how one could fix this. But it would be possible. I think. I mean, I don't know if the young disagrees, but I think it should be possible.
Yes, I think so. Use the similar idea as we do for the alternating atom mode and the molecule mode.
Yes.
You switch between two modes. Yes, that requires quite a long config file, I have to say.
Okay.
For instance, so this is really thinking off the top of my head because we're thinking of ways of changing the dynamics. And one thing that I remember seeing vaguely a couple of years back when I was looking at the literature on stress tensors is that almost all decompositions of forces give you very non-intuitive stress tensors. So there's a machinery, of course, which is completely standard. You find all the forces on all the particles and you essentially take moments of that. And that gives you a tensor, and that's the stress tensor.
Okay.
And almost all of these stress tensors are not symmetric. Which comes because the forces are not central, for instance. But you can, there are some papers which show you that you can regroup the forces to get a purely symmetric stress tensor, and essentially that's eliminating circulatory parts of the force. That essentially the normal decompositions give you non-central forces when you look at a sort of a coarse-grained picture. Okay. And what we learned from Zay is that more you've got force, more force is linked to is linked to lifting rates. And so by getting rid of these spurious parts of the force that give you the non-symmetric stress tensor, maybe this decreases the lifting rates, and maybe so this is way beyond speculatory. This is what you should do, of course, when you have a seminar, which is bringing up weird questions, which probably to which the answer is probably no. But just once in a lifetime they come up, yes. So this was the vague thought that came to me during the talk.
Yeah.
Maybe one wants to be able to redo. So this is of course this would be changing the representation, I guess, of the angular forces. In the code as it is, it's generating angular forces which give you non-central bits, and this would give you this extra strange contribution to stress tensors. And we So we'd say that the stress sensor going to zero was sort of an optimal way of running the code.
But even now we have, this is still a Python. We still call it a Python program, right? Even though there is some kind of C in it. But now, you've seen this little dancers. That was really beautiful.
Yeah.
And so we have now a rate. So particles move like 10 angstroms. On our laptops, you have 10 angstrom of motions per second, even in a system with thousands of particles. So we don't have so much. We have lots of problems, right? We have lots of problems, but we get some. So this kind of motion, what I'm just saying, this kind of, you saw this motion, and this motion, whatever the number of particles in your whole system, it's at the moment, in this very general application, is already at 10 angstroms per second.
Yeah.
Which is not bad, right? It's right, and so with Liang, we at some point we discussed, right? We all of that discussed whether we needed, because this is a kind of very general application, right? And very general application that can do lots of things. But that's what Philipp always calls Python magic, right? You call this Python magic. It is so that we have this very complicated, you can do everything, but then when you do it easier, you gain 3% of computing time, right? So we wanted to have a lightweight version of the same program, and this lightweight version saved. How much did it save? Nothing, right? It
saved something, but this was actually for hard disk simulation.
Yes. But so there's real Python magic hidden in what you just described. Comments? Butao, Yoshiko, Marco, Zé?
Philip, what's the book you mentioned in the beginning of the Python programming or organizing the programs? Well, when I write a complicated program, it's really some trouble. That will help a lot.
Sorry, I couldn't get the question.
Well, the book you mentioned in writing complicated Python program. In the beginning, you mentioned there is a book.
The design pattern book.
The Gang of Four.
Yeah, the Gang of Four. This is not specific.
That is it.
You have it already? Yes. It's not specific to Python, actually. It's very general for all languages, so you can use it in C++ if you want. It's kind of still in this object-oriented corner because it's quite old. So, I know there are some new design techniques for functional programming or so, but if you want to design object-oriented, it seems to be still valid. The Wikipedia article is also very good. Just Google the Gang of Four, and then
you can share your screen if you want to.
Yes, I can share it.
I'll search on LibGym.
Yeah, so this is German, but let me change.
Does Gang of Four work as a search term in China?
maybe Google designed it. But there, there should be a lot of links to the design patterns, which are, here you can see as patterns by type, and then you can go through them one by one on Wikipedia, and these help me quite a lot as well.
And the book is available electronically. I think it's available online. It's not.
But I think all of us bought it, right, in paper, because we were. It's kind of impressive, right? We started. When did we start this? When it was first mentioned? That was really in in August 2018, right? And we have kept with this thing throughout. I mean, we have not made any shortcuts. We have stayed with this more or less. No, I think we have stayed with this mediator thing. And another thing that also maybe Zay, you might be interested in is that we now got converted to using PyCharm. Maybe you use I mean.
Oh yeah. Maybe.
So that's. I mean, so you see, for example, you see all these names. We have event handlers, and we have trees, and there's a lot of names that you saw. Of course, these names are always the 17th version of something else, right? And there is a lot of So you introduced us to this refactoring, and then so it's so we don't write it on. This program is not written by writing code in VI, but
Yeah.
it's,
Although it would possibly be possible because Vim is very can do a lot of things by himself. But it just helps me, for example. I mean, it's just an editor which helps you a lot with this very standard things in Python. If you write a class that automatically creates the init.
Yeah, but excuse me. Well, I downloaded the package from GitHub. I found there is an install some complex package. Did you write them by your own?
There's some.
On your own. I mean, is it included in these books, or did you find it somewhere else?
I mean, what we write in our installation. I mean, no. I mean, this book really just talks about design patterns and how you then write these things on GitHub and how to install things. This is more knowledge from other packages. I mean, I think we looked a lot of how other Python packages do it, for example, NumPy, SciPy, or another one we use, and then kind of you follow their way because they are way more experienced in this than we are.
Okay. Other question? Comment? Last chance. Okay. So then let's thank Philipp again, and thanks a lot, and
Thank you.
see you again.
See you.
Okay. Thank you. Okay. All right. Thank you, and see you soon.
See you.
Bye bye.